Today, we'll be looking at the introduction to applied electricity, and we'll be looking at some fundamental concepts used in the analysis of electric circuits. So basically, we'll be looking at some terminologies that are going to be common in applied electricity, some concepts and some formulae. So first of all, we are going to quickly look at what an electric circuit is. Okay, so I have a simple electric circuit drawn here. So usually we can define an electric circuit as a closed loop pathway that allows electric currents to pass through it or to travel through it. So basically for every electric circuit, these are some common things we are going to see. So we are going to have a power source, that's this. We're also going to have a load or a resistor, and we're also going to have the pathway for current to flow. So that's like the conducting lines. All right. And I hope we all know what current and voltage is already. So current is the rate of flow of electrons in the electric circuit. And the voltage is the measure of the electric force that pushes electric charges through the circuit. All right. So moving on, we know that there are two main types of currents. We have the direct currents, that's usually represented by DC, and we have the alternating currents, that's represented by AC. So for the DC, we know that it has a unidirectional flow, but for the AC, the direction of current flow keeps changing with time. So flow direction changes with time. Okay, so next we are going to look at the types of voltage sources we have. This is just a quick review, so we are not really going into all the terminologies. You can read further for the other ones. So the next thing we are going to look at is ideal voltage source and a practical voltage source. We are going to look at the difference between them. So for the ideal voltage source, voltage source, it maintains the same voltage across the source terminals no matter the currents drawn from the terminal. So if I should have a circuit, let's see, okay, so this is my voltage source. This is a positive terminal, this is the negative terminal, and this is my load or resistor. So for an ideal voltage source, the power source, that's this, it doesn't have any form of internal resistance present. That's one thing that has to be noted. Also, the current, let's say I, flowing through, is going to flow through the circuit. We are representing it by I. And as said earlier, the voltage, let's say VL, the voltage that's going to be across is going to be the same as the one at the terminal. So if we are going to represent this one as Vs, the voltage here Vs is going to be equal to the voltage across the load, that's the VL. Alright, so moving on, we'll also look at that of a practical voltage source. So for the practical voltage source, that one has internal resistance present. So we are also going to represent it by this. Then we have our load in the circuit. We have our current I, let's say IL. We have the voltage across this VL and R, let's say RL. We are going to represent the internal resistance by RS and the voltage source by Vs. Okay, so in this case, if we are to find the voltage across the load, that's the VL in this case, our VL is not going to be equal to our Vs in this case. This is due to the internal resistance present in the voltage source. So for this case, our Vs is going to be, say, the total voltage that we can have. So Vs is going to be equal to the, let's say, the voltage loss that's going to be lost due to the resistance presence. That's the resistance Rs. So let's represent it by, let's say, V, then plus the voltage across the resistance RL. So that's VL. So in this case, to find our V is going to be, according to, V is always equal to IR. So in this case, our Vs is going to be equal to, we are going to expand this V. So we would have the internal, that V is going to comprise of the internal resistance and the current. So we are going to have our IL times our RS in that case, then plus our VL, that's the voltage across the load. So making the VL the subject, our VL is going to be equal to our Vs minus IL times Rs. So this is going to be the relation for the voltage across a resistor if we are using a practical voltage source. Okay, so next we would also look at series and parallel arrangement of resistors. So say we have a circuit drawn this way. So first of all, we are going to look at series arrangement. Series arrangement. So here we have resistor, say R1, and we have R2, and this is our voltage source. Okay, so we can say that resistors R1 and R2 are in series if one, the same current is flowing through both resistors. Same current is flowing through, and two, there is no node present. Okay, so in this case, we can see that if you know that for every circuit, the current is going to flow from the positive terminal to the negative terminal. Okay, so if we have our current I, the same current that's going to flow through I is what's going to flow through R2. R1. So the same current flowing through R1 is the same current that's going to flow through R2. and also there's no node or junction present. And when we say a node, we mean any point in the circuit where current is going to be divided. So where current is added or divided. Okay, so that's for the series arrangement. Sorry. And when we are looking at the parallel arrangement, so in that case, we are also going to look at how it can be represented. Okay, so that's a simple circuit, and we are going to use to define what how a parallel connection or a parallel arrangement will look like. So the part I've indicated with the letter A is what represents a node, because we can see that at that point, as current flows, when it gets to point A, there's going to be a division of current as stated earlier. So that makes it a node. Okay, so now moving on, for parallel connection 1, there has to be so for parallel resistors, the first thing to note is that we consider only two resistors at a time. So we consider only two resistors at a time. That's the first thing that has to be noted. And also, there has to be a node present. And two, when we are following the path, that's the flow of currents between those two resistors, we don't want to come across any other resistor or battery in that path. So that's another thing we have to know. It's only those two resistors that have to follow through that path. Okay, so those are the two main things that have to be noted. So we can move on from there. Okay, so if we are to find the total resistance, that's say RT, for series arrangements, it's always going to be the sum of the resistances that are in series. Please, I hope we get that. So this is one thing you have to note because we use it a lot. And the next is the parallel arrangement. So for that one, if we are finding the total resistance, it's usually represented by 1 over RT, that's the total resistance, equal to 1 over say R1 plus say R2 if we are looking at just two resistors, and it can further be simplified to get RT, that's the total resistance, is going to be R1 times R2, sorry, all over R1 plus R2. Okay, so those are the basic things that we have to know as we go through the course. Okay, so the next thing we are going to look at is the delta star arrangement. The delta star arrangement, delta or star arrangement. Okay, so first of all, let's look at the delta arrangement. So for the delta arrangement, it is neither in series nor in parallel. So here we are going to have, say, three resistors arranged in a form like this. So it can either be like this or this way. So here, first of all, we can realize that they are neither in series nor are they in parallel, because you realize that we have nodes present at all these points. There are nodes present at those points, and for the series arrangement, we said that doesn't have to, there shouldn't be, sorry, any nodes present as you from the resistors you are considering, sorry. And for the parallel, you are just supposed to consider two at a time. So if we are considering this resistor and this resistor, as we are looking at the path from that resistor to the other one and back, you realize that we come across this resistor, and as we said earlier, there shouldn't be anything in the path when we are traversing that path. Okay, so that makes it not parallel as well. And also, we are also going to look at the star arrangement. So this is usually the star arrangement. Star arrangement. Okay, so say you can have your resistor R1, R2, and R3 present here. So you realize in this case, they are neither in series nor in parallel. So one main thing we are going to look at here is how to convert from star to delta and also from delta to star. So we are going to keep this one. So if we have this star arrangement and we wanted to convert to the delta arrangement, let me just draw it again. Okay, so we have our star and we have our star in the black, color and the delta in the red. So first of all, we are going to look at from delta to star we are going to convert, sorry, from delta to star. So if we are going to represent the resistors, so for the delta one, we are going to represent this by R1, R2, and this by R3. And for the star, this is RA, RB, and RC. Okay. So if we have the RA, so that's the first one that we want to express in terms of. So for RA, first of all, we are going to look at the ones adjacent to the RA, and we can see that this and this, that's R1 and R2, are adjacent to the RA. So those are the ones that we are going to have as our numerator. So usually the ones that are adjacent are going to multiply each other. So that's the R1 times R2, and all over the sum of all the resistors present. So that's going to be this, and this. So all over R1 plus R2 plus R3. So similarly, if we have RB and want to convert from the delta to the star, so we first of all, as we said earlier, we are going to look at the ones adjacent to it. So for the RB, the one adjacent to it is the R2 and R3. So those ones are going to be your numerators multiplying. So that's going to be R2 times R3 all over the sum of all the delta resistance. So that's going to be R1 plus R2 plus R3. Alright, and similarly for RC, we are going to get R1 times R3 all over R1 plus R2 plus R3. Alright, so next we are going to also look at star to delta configuration. So how to convert from star to delta. Star to delta. So as I said earlier, the ones represented by black are the star resistances, and we are going to convert them to delta instead. So here R1 expressed in terms of the star would be, so in this case, once again, the ones adjacent to R1 are RA and RC. So first we are going to have we will add the ones that are adjacent. So that's RA plus RC, then plus RA, RC, all over the last one that we didn't consider. So that's the RB. So that's how you can convert from star to delta. So when you are converting from star to the delta, once again, you look at the ones that are directly adjacent to it. So that's in this case RA and RC. You get RA plus RC. You first add them, then you add the multiplication of those two all over the very last resistance, that's the RB. Okay, so we are also going to do that for R2. So for R2, the ones adjacent to R2 is RA and RB. So we are going to have RA plus RB plus RA RB all over RC. And similarly for R3, we are going to have RC plus RB plus RC R times RB all over RA. Okay, so having gotten these concepts, we are going to look at a few examples that are going to help us understand all the concepts we've learned so far. Okay, so our first example a first part, we are going to just briefly look at them as we go through the questions. So here we have 2 ohms and we have 1 ohm here and we have our voltage source here. So for this question, we were asked to find the effective resistance of the circuit. So one concept I didn't mention earlier was the concept of short circuiting. So when we say a circuit has been short circuited or a part of the circuit has been short circuited, we mean that a path of least resistance has been created for the in the circuit. Sorry. So when current is flowing through the circuit, let's say from this point we have I, there's a node here where current is going to split. So we have part of the current flowing here, part flowing here. Then when it gets to this junction, you realize that this arm of the circuit has 4 ohm resistance present, but in this particular arm there is no resistor present. So in that case, we say the circuit has been there's a short circuit because the current is going to or would want to flow through this path instead of flowing through this path. This is because for the short circuited path, there is no resistance present and it's going to easily flow through that path. Just like when a river is flowing, if there's a blockage, it would want to rather look for a path where it will be able to flow freely. So that's the same when current is flowing to is look for a place where it can flow more freely rather than a place that has a resistance or a load. Okay. So in this case, if we were asked to draw our effective circuits from this diagram, we are going to have this. So in that case, our effective circuits, that means the 4 ohm and the 5 ohm resistor are not going to be effective in that case. So this is what is going to be left of our circuits. So this would be our effective circuits. Effective circuits. Okay. So in this case, so having had our effective circuits, we are supposed to find the total resistance in this circuit. So first of all, considering the 3 ohm and the 2 ohm resistor, are they in parallel or in series? So first of all, we know that for it to be in parallel or series, we have to consider the presence of nodes, whether the same current is flowing through and all those things. So first of all, we are going to check whether they are in series. Because of the node present here, we know that straight away they are not in series. And they are in parallel because from the 2 ohm resistor to the 3 ohm resistor and back to the 2 ohm resistor, you realize that it's just those two loads that are in that loop. So we can say that it's safe to say that they are in parallel. So as we said earlier, in determining the total resistance for parallel circuits, we are going to have the total resistance for that part. So we are saying that the 2 ohm resistor is in parallel with the 3 ohm resistor. So this is the notation. This is how it's represented. So this would be equal to the first so the numerator, they are going to multiply. So we have 2 times 3 all over 2 plus 3, and that's going to give us 6 over 5. Okay, so now our circuit has been reduced to this. This is going to be our new circuit. So now that part will be reduced to 6 over 5. 6 over 5. Okay, so now there are 2 resistances left. So now there is no node present at this point. There's no node present at that point. So, and the same current is flowing through the 1 ohm and the 6 over 5 ohm resistor. Please don't forget your units when you are solving your questions. So the 6 on 5 ohm resistor and the 1 ohm resistor are in series. So our total resistance, say RT, is going to be equal to, for resistors in series, we add them. So we have our 1 ohm resistor plus the 6 over 5 ohm resistor. So here we are going to have 11 over 5, and that's approximately 2.2 ohms. So that's going to be our total resistance in the circuit. Okay. Okay. So for our next question, that's question 2. This is the circuit we are going to be considering. So we have a 4 ohm resistor connected to a 3 ohm resistor. and this a 5-volt power source and connected to another 2 ohm resistor. And then we also have this present. So as I mentioned earlier, we have to check whether there's a short circuit present in the resistor. So current is going to flow from the positive terminal to the negative. So it moves in this direction. When it gets to this point, first we check this direction. We are going to have a resistance here. And when we also check the other direction, so let's say this is path I1, this is path I2. Realize that when it gets to this junction as well, there's a resistance here, but there's no resistance in this path. Pardon me. There's a resistance here rather, but there's no resistance in this part. So you realize that instead of the current moving towards dividing at this node, instead of the currents dividing at this particular node, it is going to just move through this path, because that path provides the path of least resistance. So our effective circuit is actually going to be consisting of only the 3 ohm resistor. So this is going to be our effective circuit. So in this case, we were asked to find the current I, and from Ohm's law we know that I is equal to V over R, and that's going to be the 5 volts over the 3 ohms, and that's going to give us approximately 1.67 amperes. Okay, so moving on to the next question. Moving on to our next question, we have another, so that's question 3. We have a 4 ohm resistor, we have a 2 ohm resistor, and we have another 2 ohm resistor here, and another 2 ohm resistor here, and we have a 1 ohm resistor at this point. So here we are to find the total resistance present. So in this case, you realize that one, we don't have any short circuits present in this circuit, and this is actually going to be our effective circuit. So first of all, would consider the resistors at both ends. So you realize that the 4 ohm resistor and the 2 ohm resistor are in series, so we can add them up to get 6 ohms, and the 2 ohm resistors at this point are also in series, so we can reduce our circuits to get 6 ohms at this point. Our 1 ohm resistor is still here, and we can also have our 2 ohm, so 2 plus 2 we get 4 ohms, and the 4 plus 2 ohms we get 6 ohms. So you follow through what we are doing. So here we have 4 ohms present here. Okay, so Next, you realize that since there's a node present at this particular point, and when you traverse the path between the 6 and 4 ohms, there's nothing else there except the two of them. So these two are going to be in parallel. So we have our 6 ohm resistor being parallel to our 4 ohm resistor. So here we are going to have, as I said earlier, they multiply each other. So we have 6 times 4 all over the addition. So that's 6 plus 4. If we are considering resistors in two resistors in parallel. So here we are going to have 24 over 10, and that's equal to 2.4. Okay, so we can further reduce our circuit. So we can further reduce our circuit to get this. So that's going to be 2.4 ohms. 2.4 ohms. And now our 2.4 ohm resistor and our 1 ohm resistor are in series. So we can, our RT, or our total resistance, is going to be our 1 ohm resistor plus the 2.4 ohm resistor, and our final result is going to be 3.4 ohms. Question 4. So the next one we are going to look at, let's say our fourth question, is we have our voltage source. We have a 3 ohm resistor here. Then we have a 2 ohm resistor. And then we have a 4 ohm resistor. And we have a 6 ohm resistor here. Okay, so first of all, we check for our effective circuits, and both possible passage places for the current have resistances, and throughout there is no short circuits present, so we can move on. So first of all, we are going to start simplifying from the right hand side. That's this point. So we realize that the 6 ohm resistor and the 4 ohm resistor are in parallel. There's a node present here, and when you traverse through their path, there's no other elements present. There's just the two resistors. So 6 ohm resistor in parallel with the 4 ohm resistor, we are going to have this R1 times R, so that's the 6 times 4 all over 6 plus 4, and that's going to give us 2.4. So we can further reduce our circuits to give okay, so now the 2.4 ohm resistor, sorry, forgot to add my units. Okay, so the 2.4 ohm resistor is going to be in series with the 2 ohm resistor. So considering those two, they are in series, so we add them up. So that's going to be 2 plus 2.4 to give us 4.4 ohms. So we can further reduce our circuit. 4.4 ohms. So we realize that the 3 ohm resistor and the 4.4 ohm resistor are in parallel. So our total resistance is going to be the 3 times 4.4 over 3 plus 4.4. And when you compute that, we are expected to get an answer of about 1.78 ohms. Next, we'll be looking at another example. So we have terminal A, we have a 1 ohm resistor, we have a 3 ohm resistor here, then a 6 ohm resistor. So 1 ohm resistor, 3, 6. We have a 4 ohm resistor present here, and say another 4 ohm 4 ohm resistor, and we have a 3.3 ohm resistor, and this is terminal B. Okay, so first of all, we start from the right hand side. Our 4 ohm resistor is in parallel with the 6 ohm resistor, so we have our 6 times 4 over 6 plus 4 to give us approximately 2.4. So we can reduce that part to give us this. And we know that our 2.4 ohm resistor is going to be in series with the 3 ohm resistor. So we can sum those two up. So we have 3 plus the 2.4 ohms to give us 5.4 ohms. Okay, so we can further simplify to give us this. So we can further simplify to get this. So we have a node present at this point, and checking everything to make sure we are on track. We realize that our 4 and our 5.4 ohm resistor is in parallel, and we move on to get 4 in parallel with the 5.4. We get 4 times the 5.4 ohms all over 4 plus our 5.4 ohms, and that's going to give us, so when you simplify using your calculator, you're supposed to get about 2.298 approximately that ohms. So we can further reduce our circuits. 2.298 ohms. So we realize that our 1 ohm and our 2.29 ohms are in series. So that's going to give us 1 ohm plus our result, that's a 2.298 ohms. We are going to get 3.298 ohms. Okay, so we can further simplify. Our circuit to get this, and this is going to be 3.298 ohms. Okay, so there's a presence of a node here. Oh, sorry, my line wasn't joined properly. Okay, so there are nodes present, and our 3.3 ohm and our 3.29 are in parallel. So we can further simplify our circuit. So we have 3.3 in parallel with the 3.298. If you are comfortable with fractions, you can keep your answers in fractions throughout your solution. So here we have our 3.3 times the 3.298 all over 3.3 plus 3.298, and we are looking at getting an answer of about, if you do the computations, you are supposed to get an answer of about 1.649. That's the result you should be getting. Okay, so our next question is going to be on the star delta transformation, so that we can apply what we learned. So this is our circuit. We have our terminal A is connected to a 6 ohm, another 6 ohm, then sorry, okay, I'll be done drawing it in a minute. Okay, so we have a 6 ohm resistor, 6, here's 3, here's 3, and we also have 3 here. Okay, so here we see that we have a star arrangement present here. We have a star arrangement present in the circuit, and we also have a delta arrangement if you look carefully. So now the issue at hand is we are supposed to check whether are we going to convert the delta to a star or the star to a delta instead. So in this case, we are going to consider the star to delta first. So this is our star as I indicated. This is our star arrangement as I indicated earlier. So we are going to convert it to a delta arrangement. So this would be say R1, R2, and this say R3. R3. So R1, remember for if we are converting from star to delta, the relation is going to be, we first look at the ones that are adjacent to the one that we are considering. So R1 is going to be R6 plus 6 plus the 6 times 6 all over 3. Okay, so we are going to have 6 plus 6, we have 12, and our 12 plus 6 times 6 is 36 all over 3. So that's going to be 12, 12 plus 12. Okay, then the next one we are going to look at is R2. So our R2 is going to be, we first add them. So we have our 6 plus 3, then plus our 6 times 3. So 6 times 3 is 18 all over the other one. So that's 6. So that's going to be 9 plus 3. And we are going to have 12 in that case. In the next one, so that's the R3, we are going to have R6. So it's going to be similar to the R2. 6 plus 3 plus 6 times 3 is 18 all over 6. Then we are going to have 9 plus 3, which is going to give us about 12. Okay, so let me clear this part. Then we put in our new values. So our R1 is 24 instead. And we have this to be, our R2 was 12. We have this to be 12. And we have this to be 12 as well. Okay. So first of all, we realize that these two, that's the 3 and 12, are in parallel. So we can tackle that first. So let me clear this portion. So 12 in parallel with the 3, we are going to have 12 times 3 all over 12 plus 3. We are going to have 36 over 15. And then next part, we also see that the 24 and 6 are in parallel. So looking at that one, we can get 6 in parallel with 24. We get 6 times 24 all over 6 plus 24. So that's going to be 144 over 30. So that's about 4.8. So we can further simplify our circuit. So we can simplify this one to 4.8, and we can simplify this part to 36 on 15 divided by 15. We have 2.4 for this part. Sorry. So this is the simplified form of our circuit. So we realize that the 4.8 and the 2.4, they are in series. So we can add them up. So 4.8 plus 2.4, we are going to get that's 7.2. Okay, so we can further reduce that portion. 7.2. Okay, I think it's getting a bit messy, so let's clear. Okay, so realize that the 7.2 and 7.2 and 12.2, they are in parallel. So 7.2 in parallel with the 12. So we have 7.2 times 12 all over 7.2 plus 12. So here we have our results going to give us that's about 4.5. So we can further reduce our circuit. So last of all, we have our 4.5 and 3, and they're also in parallel. So 4.5 in parallel with 3. So our final result should give us that's approximately 1 0.8. So that should be our total resistance. So don't forget your units. It's supposed to be in ohms. Okay, so that's how we can simplify the circuit. And next we'll also be looking at another example. Okay, so earlier, I forgot something. So earlier in the question we were looking at, we had a delta arrangement, then we also had a star arrangement, but we chose the star to delta because if you convert from the delta to the star, it still doesn't simplify the circuit enough for you to continue your simplification, your calculation for the total resistance. Okay, so that's why we chose the star to delta instead. So we are going to move on to our next question. But if you have any questions, you can contact me. My contacts has already been made available, so you can just feel free and text me. Then I can walk you through if you have any issues. Okay. So the next question we'll be looking at are more simple questions. So here we are going to introduce the concept of current division. As we've already looked at it, but here we are going to calculate for the current at different points in the circuit. Okay, so we will take an example. So assuming we have 10 amperes, current of 10 ampere flowing through this circuit, we have our first resistance here with 2 ohms. Then we have our second resistor, 4 ohms. And we have our last resistor in this arm, so 1 ohm. So this is our effective circuit. It can't be further reduced, so we are going to keep it this way. And we realize that if we are to calculate, let's say, the current in this arm represented by I, we realize that when the current is flowing through, there's going to be current division at this point and this point. And you also have to note the direction. Sometimes they indicate the direction of the current. So in this case, you realize that in the question that we were given, the arrow was pointing in this direction. In this direction. So it's going to tell us whether our the current I is going to be negative or positive. So you have to take note of that. So in this case, you realize that first of all, there's going to be, as I was saying earlier, there's going to be division of current at this node and at this node. Okay, so in order to make the work simpler, we can first find since the 2 ampere and the 1 ampere resistors are in parallel, we can find the total resistance for both of them, and we can redraw our circuit to simplify it for us. So 2 parallel with 1, we are going to get 2 times 1 over 2 plus 1. We are going to have 2 over 3. Okay, and our simplified circuit is going to look like this. We have our I still here. We have our 4 ohm, and we have our reduced resistance, the parallel ones, to be 2 over 3 here. So in this case, now we know that the division is just going to happen at this point. Okay, so we realize that so let's say if we label the current, it's going to flow into So it's going to move in that direction. And let's say if we label it as I1, so we can write the formula as there. So you realize the direction in which they are moving. The 10 ampere and I are moving towards the node. So those are the ones going in. So we put them at one side. So we have I plus the 10 amperes at one point. And we also look at the current that's moving out of that direction. And that's just this one. These ones are moving towards the node. This one is moving away from the node. So we would have them being equal to I1. So that's just for us to understand the relation. So you realize that in order to find, so the question asks us to find our I. Okay, so we can make I the subject. Our I is going to be equal to I1 then minus the 10 ampere. So how do we find I1? So let's quickly take a look at that. So let's quickly take a look at that. So in finding I1, we know that I I is always going to be equal to V over R. Okay, so in this case, we know that if we were to find the total the voltage in this particular circuit, we are going to have V is equal to IR from, and that R will be looking at the total resistance, and that's going to be the 2 over 3 in parallel with the 4. That's going to give us our total resistance. So that's going to be I, and I over here represents the total current, and we have that as 10 already. So here we are finding I1. So here we have our total current, that's the 10. We have our total resistance, that's going to be 2 in parallel with 4. And if you do the computation for that one, let me quickly do it with my calculator. So we have 2 over 3. So we have 2 over 3 times 4, then divided by, so we have 2 over 3 times 4, and we also have 2 over 3 plus 4, and it should give us a final result of, that's about 0.5714. That's what we're expecting. So our total resistance one, the R1, sorry. Okay, so our R1 is the 2 over 3 ohms, and we should look at getting a value of about 8.55 approximately. Okay, so I think there's a little change in the value. So we rather have 8.571, I think. So in that case, if we come and substitute our value, our I should give us 8.7571, sorry, minus the 10 amperes. Okay, so we have to clear this part. So our I should be giving us about minus 1.429. Okay, so we are going to go through another method of arriving at our answer. So just as we did this calculation, to arrive at the value of our I1, we can do a similar calculation to get our I. So here we can just go straight away. After simplifying our circuit, we can go straight away and say our I is going to also be equal to V over the I. So the I is going through this particular load, so that's over 4 ohms. And we've already found our V. The V is going to be the same, the total current times the total resistance, and it's going to give us the 10 times 0.5714 all over 4 ohms. But what we have to notice that because the arrow is moving in the opposite direction, we have to bring a negative in front of our answer, and that's one thing we have to take note of. So we are going to get about, so that's going to be 10 times 0.5714 divided by 4, and we are going to get approximately minus 1.4285, and that's approximately 29. Okay, so that's also a shorter way to just go about the answer. All right, so moving on to our next question. Okay, so we also have another concept called an open circuit. Have 2 ohms here. So you realize in this case there's a break within our circuit. So that's at this point there's a discontinuity in the circuit, and that's what we call an open circuit. And the characteristic of an open circuit is that it has very high resistance. So the current wouldn't even want to pass through that part. It will go through the path of least resistance, as I said earlier. And since the open circuit has a very high resistance, it wouldn't want to pass in that direction. So in this case, if we were to draw our effective circuit, we are going to have, so here the current is not going to go in this direction, but it's rather going to go in the other direction. Okay, we have our 5, we have our 7 volt, and we still have our 2 ohms here. So this is what our effective circuit is going to look like. So here we can further simplify. We can see that our 4 and our 2 ohms are in parallel. So 4 in parallel with 2, we are going to get our 4 times 2 all over the 4 plus 2, giving us 8 over 6. So here we have the circuit further simplified to give us this. So 8 over 6 can be further simplified to 4 over 3. And our 4 over 3 is going to be in series with the 5. So our total resistance is going to be our 5 plus the 4 over 3. So in this case, we are going to have about 19 over 3 as our final answer. So in this case, if we were asked to find the current flowing through, let's say, the circuit, we are just going, the total current is going to be our voltage V over our total resistance RT, and that's going to be equal to over 19 over, sorry, I think I have to come up. So it's going to, our I would have been equal to V over R, giving us our 7 over 19 on 3 to give us our current. So that's if we had a case of an open circuit. Okay, so you can simplify to get the value for the current. Okay, so we are going to look at another example here. Another interesting example. Then we look at, okay, 2 more examples. We are going to look at one more delta star transformation question and another simplification question. Okay, so the question is as follows. So here, all the resistors present are of value 1 ohm. So I want you to take time and try the questions too, and not just write out the solutions. So all the resistance present in this value, in this diagram, sorry, are of value 1 ohm. So each resistor is equal to 1 ohm. Okay, so first of all, we can simplify this part. We can see that both of them are in series, and 1 plus 1 is equal to 2. Let me just indicate the values. They are all value 1, 1, 1, 1. So 1 ohm each. So they all have a value of 1 ohm. So looking at this particular point, as I've mentioned earlier, these two sections are these two 1 ohm resistors are in series, so we can add them up to get 2. So we can reduce that portion of the circuit and just label it as 2. So now we've added them to get 2 ohms. 2 ohms. And similarly, this part, these two resistors are also in series. So 1 ohm plus is equal to 2. So we can simplify that section to also give us 2 ohms. 2 ohms. Okay. So next, you can also simplify this portion of the circuit. So we realize that these two portions of the circuit are in parallel. So we can also take care of that one. So we have 1 in parallel with 2, and that will give us 2/3. If you simplify, you are going to get about 2/3. So we can reduce our circuit to give us 2/3 at that point. 2/3 ohms. So now next, we are going to have a so if you look closely, now we have a star arrangement present here, because now you realize that even when we move this way, we don't find any um when we look through the circuits we have left, we don't have any that are really in parallel or in series, but we can actually see a star arrangement, but still it can't be simplified easily. So we can convert it to a delta format to see whether we can simplify it more. So this one we are going to look at star to delta transformation. So we are going to indicate it this way. And we are going to have one more in this direction. So let's say we are going to have R1 here, R2, and R3. So R1 is going to be equal to, we are going to have, as I said earlier, you are going to look at the ones that are adjacent to the one you are looking for. For star to delta, we are first going to add the ones that are adjacent, then plus the products of those two. So 1 times 1 is 1 all over the last one. That's the one that's far away. So here we are going to have 2 plus 1 basically, and that's 3. And that's going to be similar for all the other ones too. So R1 is going to be equal to R2, and it's also be equal to R3. So we can further simplify our diagram. Uh, Okay, so and we are going to change these values as well. They all have a value of 3 ohm now. After our calculations, that's what we had. So we are going to get 3 here, 3 here, and 3 here as well. And this is still 1 ohm. We've not yet come to that part. Okay, so now we can check whether we can now continue to simplify. Realize that after the star to delta transformation, we have these two sections to be in parallel now. These two portions are also in parallel. So we can further simplify those two. So first we have 3 in parallel with 2, and we are going to get